Hi everyone, I'm Aizierjiang. Thank you for being here. Today I'd like to talk about a very practical tension in federated learning. The methods that fix its biggest statistical problem tend to double its biggest system cost. Our work, which we call MB-LSGD, Momentum Buffered Local Stochastic Gradient Descent, asks whether that trade is really necessary. We correct client drift while sending exactly the same bytes per round as plain FedAvg. Let me show you how. Here is the roadmap for the next 20 minutes or so. I'll first spend a few minutes on why client drift is a problem and why the existing fixes are expensive. Then I'll walk you through our method. The core idea fits in one equation, so don't worry. After that, I'll briefly summarize what we can prove about it, and then spend the rest of the time on experiments on CIFAR10 and TinyImageNet, including the cases where things get subtle. Let's dive in. So first, why does this problem matter? In federated learning, we want to train a single global model over M clients, phones, hospitals, edge devices without ever moving their raw data. Formally, we minimize the average of the local objectives, where each client's objective is just its expected loss on its own data. That's the equation you see here. The defining system constraint in this setting is that communication is far more expensive than local computation. The classic answer is local stochastic gradient descent, better known as FedAvg, federated averaging, instead of synchronizing after every gradient step. Each client runs k local steps, and only then does the server average the models. That immediately buys you a factor of k fewer communication routes. But, and this is the catch, and at the bottom that we show here, this efficiency degrades exactly where federated learning is needed most. When client data is heterogeneous, what we can name it, or we call it usually as non-IID, and in practice, that is very often the case. So what exactly and actually goes wrong? When data is non-IID, each client's local objective is different from the global one. During those k local steps, every client is quietly working toward its own local optimum rather than the global one. This is what the literature calls client drift. And the equation here summarizes it. It's the accumulated gap between local and global gradients along the local trajectory. Two things to note here. First, the drift grows with k. The more local work you do, the worse it gets. And with the heterogeneity level, which we measure by a constant g-square. Second, the more importantly, it produces a bias that does not vanish over rounds, unless you decay the learning rate towards zero. And just to make non-IID concrete, this is the actual label distribution we use in our experiments. A Dirichlet partition with concentration 0.1 over 100 clients. Most clients see only a couple of classes. This is the regime we care about. Of course, we are not the first to attack client drift. The table gives you the landscape. The gold standard is scaffold, which corrects drift with control variates, and it works, but the client has to ship its control variate along with the model, which roughly doubles the per round payload. Regularization methods like FedProx and FedDyn keep the payload at one model, but they bring sensitive hyperparameters and extra compute. Momentum-based methods, FedCM, MIME, STEM, FedAcg, can need server-side statistics, and as we will see later, some of them become unstable when only a few clients participate each round. FedDC tracks the local global gap with an auxiliary variable, and proc_skip gets to zero payload through randomized communication. So the question we ask is the one at the bottom. Can we get scaffold-style drift correction while sending 0 extra bytes? Nothing beyond the model FedAvg already sends. Our answer is yes, and it comes with 3 contributions. First, drift correction at 0 payload. MB-LSGD runs on exactly FedAvg's communication budget. No auxiliary state error crosses the network. And second, we identify and fix what we call the half-step bias. If you build a drift estimator naively as an exponential moving average of what you observe, it converges to only half of the correction you need. Our additive update rule removes that bias, at least under a linear approximation. And third, we prove a convergence bound of order 1 over the square root of MKR for smooth non-convex objectives. And the bound explicitly couples the buffer rate alpha with the participation rate P, which turns out to be exactly the guidance you need to turn this method in practice. Now let's look at how it actually works. Start from a thought experiment. If a client could add a correction term C sub m to its local gradient so that in expectation it follows the global gradient, what would that term be? The answer is immediate, and it's the boxed equation. The ideal correction is the global gradient minus the local gradient. If every client had this, the local updates would match the centralized direction in expectation, no matter how heterogeneous the data is. Heterogeneity would simply stop mattering. The problem, of course, is that no client knows the global gradient, and transmitting everyone's gradients to compute it would blow up exactly the bandwidth and privacy budget we are trying to protect. So here is the MB-LSGD idea in one sentence. Each client maintains a local drift buffer U sub R super M, and that estimates this ideal correction and adds it to every one of its k local steps. The buffer stays fixed within a round and acts like a control variable steering the trajectory. The whole question now becomes, how do we update this buffer without communicating anything extra? And here is the key observation of the paper. The aggregated model that the server broadcasts away, W sub R plus 1, already encodes global gradient information. We just have to read it out. Concretely, we define 2 pseudo gradients. The global effective step is how far the global model moved this round, divided by eta k. The local effective step is the same thing for the client's own model. Notice that everything in this formula is already sitting in the client's memory. It knows last round's model, it receives the new global model anyway, and it obviously knows its own final iterate. So both quantities are computable locally with no extra communication whatsoever. Under full participation, the global pseudo gradient is exactly the average of the local ones. That's an identity, not an approximation. And for a reasonably small learning rate, these pseudo gradients track the true gradients at the start of the round. The global one approximates the global gradient, and the local one approximates the local gradient plus the buffer that was applied during the round. Subtract the 2, and look what you get. The difference is the ideal correction minus the current buffer. In other words, It's precisely the part of the drift the buffer has failed to correct so far. That is exactly the error signal we need. Given that error signal, the update rule is almost embarrassingly simple. Left box, new buffer equals old buffer plus alpha times the residual. Just accumulate the residual drift, scaled by a buffer rate alpha between 0 and 1. But there is a subtlety here, and it's one of our main contributions. You might be tempted to do the seemingly natural thing instead. The right box, an exponential moving average of the observed differences. Here is the trap. The local pseudo gradient already contains the buffer you applied. If you work out the stationary point of EMA version, you find it satisfies 2u star equals the ideal correction. So the naive estimator converges to exactly half of the correction you need. It permanently undercorrects. Our additive rule doesn't have this problem. Its stationary condition recovers the full correction, at least under a linear approximation of the trajectories. One more word on alpha. Setting it to 1 tries to fix the whole observed error in a single round, while smaller values smooth the estimate over round and are much more robust to stochastic noise. Values about 1 overcorrect and oscillate, so we never use them. The update is related to client-side momentum. Chen and her colleagues studied that before. What is new here is the explicit coupling between alpha and the participation rate, and the evidence that when alpha is tuned so that coupling matters and training stays stable under high noise and partial participation. Let me put the whole algorithm on one single slide here. Now with partial participation, which is how this would actually run, 4 steps. 1. The server samples a fraction p of the clients and broadcasts the current model. 2. Each sampled client runs its k-corrected local steps and sends back only its model. I want to emphasize this. The payload is one model exactly like FedAvg. 3. The server averages business as usual. 4. Each participating client updates its buffer locally using the pseudo gradient residual. Everyone else simply keeps their buffer unchanged. 3 remarks. Buffers start at 0, so the first round is plain federated average. Under full participation, the buffers always average to 0. That follows directly from the aggregation identity, so the corrections steer individual clients without biasing a global average. And under partial participation, a given client only refreshes its buffer about once every 1 p rounds, which that staleness is not a detail, is 1 over p. It tightens how aggressive you can be with alpha, and our theory makes that precise, which brings me to the analysis. So we can actually prove about this, but how and what can we prove? I will keep it in 2 slides. The analysis here mainly lies in standard assumptions, L smoothness, unbiased stochastic gradients with variance sigma squared and bounded heterogeneity g squared, and it tracks one central quantity, the buffer error E sub r super m, the gap between each client's buffer and the ideal correction. The first lemma bounds how far local iterates wander from the round start model. In vanilla local stochastic gradient descent, that deviation is governed by the heterogeneity g squared. Here, and this is the point I want you to take away from this slide, g squared does not appear in the bound at all. The deviation is driven by the stochastic noise and by the buffer error instead. So if the buffers are accurate, heterogeneity simply drops out of the local dynamics. The second lemma shows the buffers do become accurate. The buffer error contracts geometrically with factor 1 minus alpha p over 2 plus lower order noise terms. Notice how the concentration speed is exactly the product of the buffer rate and the participation rate. This is where the two get coupled, and that coupling propagates into the main theorem. Combining the two lemmas through Lyapunov potential, objective value plus scaled buffer error gives our main theorem. The bound has four terms: the Ural initialization term, a variance term, a heterogeneity term, and a tracking term that depends on alpha and p. Three consequences. First, the standardized step size choice. The rate is order 1 over the square root of mkr that matches centralized mini batch SGD, SGD up to constants, and it matches scaffold's order without transmitting any control variates. And second, heterogeneity decoupling. Look at where g squared sits. It's divided by r, so it's a transient term. It slows down the early phase while the buffers are still learning their local biases, but it does not set the asymptotic error flow. For FedAvg, it does. That's the quantitative difference. And third, the alpha p coupling gives the concrete tuning advice. Optimizing the bound suggests alpha on the order of 1 over square root of k, and in particular under high noise and sparse participation you want alpha strictly below 1. With alpha equal to 1, the buffer swallows the stochastic noise of every single observation. Keep this in mind, because it will explain what we see in the ablations. So much for the theory. Does it hold up in practice? Well, that's a very nice question. Our setup follows the standard non-IID benchmark protocol. 2 tasks, CFAR10 with a simple CNN and tiny ImageNet. 200 classes with a ResNet 18. In both cases, we partition the data over 100 clients with a Dirichlet concentration of 0.1, which is the strongly skewed distribution I showed you earlier. We run 200 communication rounds, sampling 10% of clients per round. Each selected client does 5 local epochs with batch size 256, learning rate 0.01, and gradient clipping at norm 10. We compare against FedAvg, Scaffold, FedCM, and ProcSkip. And one accounting note: so the communication numbers are unambiguous, we count dense 32-bit payloads with no compression, and Scaffold uploads both the model and its control variant update, so it pays double per round. Here are the CFAR10 results. Let me start with this speed column, and you'll see it does not favor us. ProgSkip is the first to reach 60% accuracy and round 144. FedAvg follows 147. We get there at 159. Scaffold at 168. So we are not the fastest out of the gate. But look at the peak versus final columns, because that's the interesting story. Every other stable method peaks and then degrades. ProgSkip peaks at 63.1 and ends at 58.3. FedAvg drops about 3 points, Scaffold about 2.5. MB-LSGD is the only one method whose final accuracy equals its peak, 61.67%. No late stage decay at all. And that makes it the best final accuracy on the slide. In a real deployment, you usually live with the model you have at the end, not the best point it happened to pass through during training. And the coast column. We do this with 8.57 gigabytes of total upload, identical to FedAvg, half of Scaffold's 17.13. You will also notice FedScience, it diverged under this setting, peaking at 30% and collapsing to 11. I will come back to why. On the larger task, the benefit of drift correction comes through more clearly. MB-LSGD reaches the highest peak accuracy, 48.37%, ahead of Scaffolds at 47.49, and we do it at half Scaffold's bandwidth, 90 gigabytes versus 180. The zero-payload baseline without drift correction. FedAvg and ProgSkip plateau around 40 to 41%, so we are about 7.5 points above FedAvg at identical communication cost. FedScience again diverged. The accuracy versus bytes view on the right makes the efficiency picture very virile. Our curve sits clearly above Scaffolds because every byte simply buys more accuracy. Let me translate those bytes into time, since this is a system audience. And over 200 rounds, we save 8.56 gigabytes on CFR10 and 90.17 gigabytes on Tiny ImageNet relative to Scaffold, a 50% reduction at matched or better accuracy. Modeling round time as compute plus communication. Our corrected update adds literally one vector addition per local step. So compute time matches FedAvg, and at matched compression, Scaffold's communication time is roughly twice ours. For the Tiny ImageNet workload, about 45 megabytes per client per round, around 451 megabytes across 10 sample clients. That means in the communication bound regime typical of cross-silo and edge deployments, say 10 to 100 megabytes per second of uplink, the end-to-end completion time improvement over Scaffold approaches a factor of 2. And against FedAvg and ProgSkip, we coast essentially the same time per round while reaching clearly higher accuracy on the larger task. Now the ablations. All on Tiny ImageNet. And these deserve a careful reading, because there is a subtlety here that I want you to see exactly as we saw it. And panel A, the buffer rate in independent ablation runs, the small buffer rate alpha equals to 0.1, stably to about 47%, while alpha equals to 0.5 and alpha equals to 1 degrade sharply, down in the mid-20s. That's exactly the small alpha regime our theory favors. Remember, alpha of order 1 over root k, our main experiment did score 48.37 at alpha equals to 1, but we regard that as a lucky outlier under the very high run-to-run variance of this regime. So our practical recommendation is clear. Use a small alpha, not 1. And for panel B, heterogeneity at the extreme Dirichlet 0.01, the run gets stuck near 10% at 0.1, we reach the 48 we saw, and at the middler 0.5, this run reaches 34%. The early phase slowdown as the heterogeneity grows is exactly what the transient G-square term predicts. And for panel C, participation is non-monotone. 5% gives 27.6, 20% gives 27.2, while the default 10% run reached 48. That looks odd. Shouldn't more clients help? And it deserves a real explanation, not a hand wave. So let's give it one right now. The intuition says more participants should mean a lower variance, aggregate, and better accuracy. So why did 10% beat both 5 and 20? Two coupled effects, both specific to stateful methods, and neither of them is unresolved drift. First, our step size condition. Eta at most P alpha over 4 LK tightens as P decreases. We held eta and alpha fixed across the sweep. So a learning rate that's admissible at one participation level can fall outside the valid range at another. And the per round dynamics shift exactly in the direction the bound predicts. Second, the participation rate changes how often each buffer is refreshed. The expected return interval moves from roughly 1 over p rounds toward every round, and the residual term 1 minus alpha over alpha p couples the two, so holding alpha fixed while varying p moves the tracking error for non-monotonically. The bottom line, once you retune eta and alpha for the target participation level, the dependence becomes monotone again, matching the standard intuition. It's a sensitivity of fixed hyperparameter sweeps, not a flaw of the drift correction. One more sanity check before I turn to limitations. Does the buffer feedback loop ever destabilize the optimization itself? This plot shows the gradient norm evolution over 200 rounds on both datasets. The point is simple. All four stable methods, FedAvg, MB-LSGD, scaffold, and proxskip, keep their gradient norms bounded throughout training. There is no explosion, and MB-LSGD's stability is comparable to scaffolds. FedCM is omitted from the plot because its gradient behavior is divergent. So the answer is no. The buffer feedback loop does not destabilize the optimization dynamics. This slide gathers the stability story and the limitations. First, why does FedCM diverge while we want? FedCM accumulates a global momentum direction across rounds under strong heterogeneity and 10% sampling. That accumulated direction goes stale and biased. Our buffer instead tracks the current round local versus global drift signal. It never accumulates stale global directions, so it avoids that failure mode by construction. And second, the limitation stated plainly here, MB-LSGD needs order the extra memory per client for the buffer, the same footprint as scaffold and main. Fine if a client can hold one extra model copy, a real constraint on tiny device. The method is stateful, so in cross-device fleets where a client may show up only once, you'd need a stale buffer policy. Periodic reset, warm restart, which we leave to future work. And during the transient phase, while buffers are still learning, the behavior is close to plain local stochastic gradient. Let me wrap up. 4 things I'd like you to remember. 1. Client drift can be corrected using only the information FedAvg already communicates. The aggregated model itself at 0 additional payload. 2. If you build that estimator naively as an EMA, you silently lose half the correction, and additive rule fixes it. 3. We proved the 1 over root MKR rate with an explicit coupling between buffer rate and participation rate and heterogeneity demoted to a transient term. 4. Empirically, the highest final accuracy among all stable baselines on both benchmarks at half of a scaffold's bandwidth, which approaches a 2 times completion time improvement whenever you are communication bound. The code is publicly available at the GitHub link shown here. And thank you. Thank you very much for your attention, and I'm happy to take any questions. And if anything comes to mind after the session, the address on the slide, Aizierjiang@outlook.com, reaches me directly. I'm glad to continue the conversation by email. And these are the references that I used while making this slide. Thanks for watching. I'm Aizierjiang. Thank you.